This video is about simulations using R. I will explain simulations using this problem, which I have taken from this book, Business Analytics Communicating with Numbers. So the problem is a company makes pullover jackets. The manager wants to do simulations to determine the most appropriate staffing level. So they have up to 6 tailors and they want to determine how many tailors would maximize profit. Demand is normally distributed. Average is 139 for demand and standard deviation is 14.61. Material cost is also normally distributed, whereby average is $12 and standard deviation is 1.37. Weekly production is uniformly distributed and ranges from 31 to 41. Weekly wage per tailor is fixed, $700. Weekly overhead cost is also fixed, $800, and selling price for each jacket is $50. I have explained this problem in great detail in another video that's about simulations using Microsoft Excel. I would strongly recommend that you watch that video first to understand the problem and formulas used in this video. The link of the video is given in the description. This is RStudio. And the first step to simulation is this code, that's set.seed, 1 in parentheses. We use this code to get consistent results. I will explain this in a few minutes. The next step is to create random values for those parameters. So we have this demand and we know demand is normally distributed. This is the code to create normal distribution or norm. This pop-up suggests n, which means number of random numbers to be generated, followed by mean and then standard deviation. R will suggest it and we can pick up these suggestions. So the first thing is n, which means number of random numbers to be generated, and in this case I want to generate 100 random numbers, so 100. Mean in this case was 139 and standard deviation is 14.61. And if you want to see what type of output it gives, I will use this command print demand. It has created 100 random numbers. Now in the next step I want to round off these numbers. For that purpose I will use this command, that's demand is equal to round, and then this demand, it comes here, and then digits is equal to 0, which means I want to round off these numbers to 0 decimal places. And if I run this command and if I print it to see how they look like, I will use this command print demand. Over here the last number was 149.4204. but once it's rounded off it becomes 149 only. All these numbers, they had 4 decimal places but they have been rounded off here. The next step is to create 100 samples for production rate, which is uniformly distributed. Demand is normally distributed, material cost is normally distributed, but production rate is uniformly distributed. And the formula for this one is sample 31 to 41, that's a range, and then we want to create 100 samples and replace is equal to true. R will provide a pop-up. It shows that the code will be X, which means our value, which in this case will be 31 to 41, size, how many random numbers I want to generate, and replace is equal to false or true. So this command means that we want to generate 100 random numbers between 31 and 41, replace is equal to true, which means if I generate a random number, suppose that random number turns out to be 35 in my first draw, and for the second draw, that random number, I put it back and then I take a second draw. And then every time I draw a sample, I will have to put it back before the next draw. And the last one is material cost, and material cost is we want to generate 100 random numbers whereby average is 12 and standard deviation is 1.37. I run this command. If you want to see how they look like, I will use this command. These are random numbers generated and I want to round them. And if you want to see how these rounded numbers look like, I will use this command. I will print it out. This is our original material cost with 6 decimal places, and this is a rounded material cost. Then the next thing is our variables, which are constant, for which there is no probability distribution. They are fixed. For example, price is fixed, overhead cost is fixed, and wage cost is fixed. So we don't need any probability distribution. We will use them as such, and I will run them. This formula has been discussed in great detail in another video that's about using Microsoft Excel for simulations. Profit calculation is our objective. We want to see how much profit we will get if we use only 1 tailor, 2, 3, 4, 5 or 6 tailors. The formula for profit is that the first step is revenues. This highlighted part is our revenue. The formula for revenue is price per unit multiplied by minimum of demand or production. Whichever is minimum, we will choose that and multiply that price per unit, and that will give us revenue. And from that revenue, we will subtract overhead cost, and we will also subtract labor cost, which is wage per tailor multiplied by number of tailors. And the last thing that we will subtract from our revenues is material cost. So this is material cost, which is material cost per unit multiplied by number of tailors and multiplied by production rate per tailor. This is the code that we will be using for simulation, and this code comprises 2 parts. This part is the same part that's profit calculation, which I just explained, and this part, it means that we want to apply it to 6 tailors. This code will display our results for individual tailors. I will select all this, and if I run it, so here are our results: 1 tailor, 2 tailor, 3 tailor, 4 tailor, 5 tailor and 6 tailors. We have to make a decision how many tailors you want to work with. So if we look at the first tailor, as you can see, the maximum value is very low, that's only 140, and minimum value is also very low, so which means we can safely exclude 1 tailor option. The second option is that whereby maximum is 1080, but in case of 3 tailors, the maximum value is almost the double of this one, so which means we can also exclude 2 tailor options and choose 3 tailors option. In case of 4 tailors, maximum is 2650 and minimum is 34, and mean value is 1391. In case of 5 and 6 tailors, we have more extreme numbers. Minimum values are very low, which means risk is very high, and also mean values are also very low. So for example, over here, mean is in 3 digits. On the other hand, mean in these cases is in 4 digits. And in case of 6 tailors, mean is in negative. So this means that we can also exclude 5 tailors option and 6 tailor option. Now we are left with these 2 options, 3 tailors or 4 tailors. Another thing that we can do is we can calculate standard deviation, which one has lower standard deviation, and for that purpose I'll be using this command. So this is a command which means standard deviation. Our profit results in square brackets 3 and 4, which means I want to calculate standard deviation with 3 tailors option and 4 tailors option, and if I run this command, it gives us this one. It shows that standard deviation with 3 tailors is 377, but much higher in case of 4 tailors. So we can choose either tailor 3 or tailor 4. Now the next part is whereby we change some of these values. For example, over here we have overhead cost is $800 and wage cost is $700. Now if we change these 2 variables, and if we make overhead cost 900 and wage cost 550, and price remains the same and everything else remains the same, and we want to determine what would happen in this scenario, let me run this command, and as you can see, the formula also remains essentially the same. If I run this command, it gives us this answer. 1 tailor option is not very much feasible because maximum value is very low and minimum is in negative. 2 tailor option has a maximum value of 1280, but in case of 3 tailor, it's almost the double, so which means we can eliminate 2 tailors option in favor of 3 tailors option. 4 tailors option, we have maximum of 3140 and minimum is low. In case of 5 tailors option, Although maximum value is quite high, but minimum value is also very low, and mean is also low compared to Four Taylor's option. In case of Four Taylor's option, our mean is 1979, but over here mean is only 1051. It means that Four Taylor's option appears to be a better option. And in case of Six Taylor's option, that does not sound reasonable because the minimum value is very low and mean value is only in 2 digits. That's only 35, which means we can eliminate Six Taylor's option. Three Taylor's option has lower standard deviation compared to Four Taylor's option. I can also calculate standard deviation for Five Taylor's and Six Taylor's option. One last thing that deserves some explanation is this code that we write at the top, which means set.seed and then 1 within parentheses. We use this code to generate consistent numbers. When you are doing simulations, there might be some problem with your code. And when you want to determine if there's a problem with the code, you want to keep your results consistent so that you can determine if there's a problem with code or problem somewhere else. So therefore, we use this code. For instance, when I run this command, it gives me these results whereby in case of first Taylor, it is -353. If I run it again, it gives me the same answer, that's -353. So as you can see here, it was -353 first time, and when I run it second time, it gives me again -353. All other values also remain the same. If I run it third time, again it gives me the same answer. If I run it fourth time or fifth time, these answers remain the same. So using this code, we can determine if our code is correct or incorrect. Now if I delete this and I run this command, it gives us this result, -415, which is different from the one we got earlier. If I run this command one more time, this time it gives us -353. So initially it was -415 for in case of one Taylor, the minimum value, but over here it becomes -353. If I run it one more time, then it's a -348, which is different from the earlier one. When I do not use this code, that is set.seed, it keeps changing results, and in this case it will be very difficult for me to determine if there's a problem with my code or not.